All right, today we're diving into a real powerhouse of a data structure, one that's a huge deal in coding interviews and a total workhorse for network algorithms. We're talking about the disjoint set union, or as it's often called, union find. Let's get right into it.
So picture this. You're building a massive social network, or maybe you're analyzing a huge computer grid. You've got millions, maybe even billions of items, and you need to answer one simple question over and over again. And you need the answer now. Are these two things connected? Not just directly, but maybe through a super long, winding chain of other items. How do you do that?
Well, the secret to pulling this off is DSU. It's this incredibly elegant, super efficient data structure that was designed for exactly this kind of problem. And trust me, getting your head around this is absolutely crucial, not just to ace interviews, but to solve a whole class of real-world connectivity puzzles. Okay, so first things first, let's really dig into the specific problem DSU was born to solve. So what is a disjoint set union? At its core, it's just a way to keep track of a bunch of items that are split into different groups, or sets. Now, the key word here is disjoint. It just means that no item can be in more than one group at a time. That's it. Its entire job is to know who belongs with who. And honestly, the absolute best way to visualize this is to think of it like a forest of trees. Seriously. Imagine each group is its own tree, and every item is just a node in that tree. The very top of the tree, the root, well, that's like the unique ID for the whole group. All any node has to do is remember who its parent is. And the root, it's its own parent. Okay, so we've got this forest, right? Now, to actually do anything with it, we only need two main moves, two fundamental operations.
First up is find. It's exactly what it sounds like. If you want to know what group an item belongs to, you just start at its node and keep climbing up, following the parent pointers, until you hit the root. That root is the group ID. Simple. Then you've got union. This is how you connect things. To merge two different groups, you just find the root for each of them, and then you make one root the child of the other. Boom, two separate trees just became one big tree.
Super simple, right? Well, there's a catch. And it's a big one. If you're not careful about how you connect these trees, you can accidentally create these crazy long stringy chains. And if that happens, a find operation could mean you have to walk up that entire long chain, which is super slow. It totally defeats the purpose of being fast.
But don't worry. This is where things get really clever. There are two game-changing tricks that turn this potentially slow approach into something that feels like magic. Let's break them down.
Yeah, this visual says it all. We do not want those long, stringy trees on the left. No way. Our goal is to keep our trees short and bushy, like the ones on the right. Why? Because in a bushy tree, the path from any node to the top is super short, which means our find operations are going to be lightning fast. So trick number one is called union by size, and it's beautifully simple. It's just a rule you follow when you're doing a union. All it says is, always attach the smaller tree to the root of the bigger tree. That's it. This one little rule does an amazing job of keeping our trees from getting all tall and unbalanced. Union by size is a huge improvement, for sure. But the real secret sauce, the thing that gives DSU its legendary speed, is trick number two, path compression. This is where the performance just leaps off the charts. So check this out. When you do a find operation, you're already walking up the tree to find the root, right? Path compression just says, hey, while you're at it, do a little bit of cleanup. For every single node you pass on your way to the top, you just rewire its parent pointer so it points directly to the root. What you're doing is flattening the tree on the fly. It's this tiny investment of work one time that pays off big time later on. Because the very next time you search for any of those nodes you just fixed, the trip to the root is just one single hop. It's this brilliant, beautiful idea of making things better as you use them.
All right, so we've got union by size and we've got path compression. What happens when we put them together? Well, you get a performance boost that is, honestly, it's almost hard to believe.
The time complexity when you use both of these tricks together is called O of alpha of n. That's alpha of n. Okay, I know what you're thinking. That looks super intimidating. But here's the crazy part. The inverse Ackermann function, that little alpha symbol, it grows so ridiculously mind-bogglingly slowly that for any number of items you could ever realistically store in a computer, its value is less than 5. For you and me, it's basically constant time. This table really puts it all into perspective.
Look at the difference. If you use no tricks, you're stuck with a slow, linear time in the worst case. If you use just one of the tricks, you get a much, much better logarithmic time. But when you put both of them together, you get that near constant time performance. That's the magic. So that's the how. It's awesome, it's fast, but where do you actually use this thing? Let's talk about the real world and, those coding interviews.
You'd be surprised how often DSU is the hidden engine behind some really famous algorithms. It's the absolute key to Kruskal's algorithm for finding the cheapest way to connect a bunch of points. It's also the best tool for spotting cycles in a graph or for counting how many separate islands of computers you have in a network. Anytime you need to group stuff and check connections on the fly, DSU is almost always the right answer.
Okay, pro tips for when this comes up in an interview, and it will. Listen up. 1. Always find the root of each item before you try to union them. 2. Sometimes it's better to implement path compression with a loop instead of recursion to avoid crashing with really deep trees. 3. Remember that the size or rank is just a guideline to keep trees balanced, not the exact height. And finally, know its main weakness. The basic DSU is not built to handle deleting things efficiently. So let's bring it all home. The takeaway here is pretty clear. Disjoint set union is just a masterclass in smart algorithm design. It takes a really simple concept, a forest of trees, and then turbocharges it with two brilliant tricks, union by size and path compression, to solve a really fundamental problem at a speed that is practically instantaneous. And that kind of leaves us with a bigger question to chew on, doesn't it? The core magic of DSU is just about maintaining emerging groups as efficiently as possible. So what other tough problems out there, maybe not even in computer science, could suddenly become a whole lot simpler if we just found the right, clever way to group things together?